Welcome to the Photoelectric Effect Part 1. Before we get started with this lesson, I want you to have both this video open in your browser, and I also want you to have the Photoelectric Effect simulation downloaded and ready to go back and forth during the discussion. In order to do that, go to the Photoelectric simulation link on my class webpage. And when you click on that, this website right here will pop up, and what you need to do is download this simulation, which will end up looking like this. After you got it downloaded, you should see something that looks like this. Okay, I'll instruct you when we get that far how to change the various parameters that are all on here. But before we proceed, I want you to have this video open in one tab of your browser, and also to have this simulation up and ready to go for discussion. So please pause this video, and at this time, take care of that. All right, now that you're ready to go, let's talk about the photoelectric effect. Let's start off with what is the photoelectric effect. The photoelectric effect, just as its name applies, photo means light, electric implies electrons, and of course effect. The photoelectric effect is the effect of light removing electrons from a metal. If we take a look at this apparatus, we are going to start off with, in this video, talking about the rate of emission of photoelectrons. In other words, this apparatus is used to measure what is called photocurrent. Here's how this apparatus works. We have two parallel plates connected to a power supply. The left side is connected to the negative terminal of the battery, and the right side is connected to the positive terminal of the battery. The left plate, therefore, is negative. The right plate, therefore, is positive. The negative plate called the cathode, the positive plate called the anode. The light in the photoelectric experiment is shown on the negative plate. The light, if the frequency is great enough, we'll talk about that later, kicks electrons off of the metal, and because electrons are negatively charged, they are repelled by the negative plate and attracted to the positive plate. So they go over here to the positive plate, move through the circuit, pass through this microammeter because we're measuring a very small amount of current. I'm not talking about a lot of current here. And electrons continue on through the circuit and go to the positive terminal of the battery. The battery does work, puts the electrons back on the negative terminal, which puts the electrons back on the negative plate, and the process continues. So this is how this apparatus measures what is called photocurrent. Or in other words, it's measuring the rate at which electrons are being ejected from that metal. Okay, pretty ingenious little apparatus. Now we need to talk about what experiments were done with this apparatus and what they proved. Okay, so we have our light of varying frequency or intensity shining on the metal, producing photocurrent. All right. Two things were studied here. One of the things that was studied was how does the effect of intensity of the light, what would be another name for the intensity of light? The brightness of the light. How does that impact the amount of electrons being ejected from the metal? Well, electromagnetic wave theory would predict that brighter light, more intense light, is light that has greater amplitude. Now we have to go back to our study of waves. What does amplitude indicate? The amplitude of a wave indicates how much energy the wave is carrying. So it should make sense to us that a wave theory person would say light that is brighter, it is brighter because its amplitude is greater and it's carrying more energy. So brighter light, more energetic light that is hitting this negative plate is removing more electrons from the metal. So they experimented with that. Well, if they're going to vary intensity, start off with dim light and get brighter and brighter, what aspect of the light do they have to keep constant? And of course, the answer to that question is you have to have the frequency controlled. You can't have both the brightness and the frequency being varied at the same time because you wouldn't know which one is impacting the rate of emission of photoelectrons. More on the results here in a moment. The other aspect of this, they wanted to figure out, okay, how does the frequency of the light affect the rate of emission of photoelectrons? Well, what is a wave person's perception of frequency? Of course, that would be color. So if they're going to vary the frequency, vary the color, we have to hold brightness constant. Brightness intensity would have to be our control. So what was the outcome? When intensity was varied, when the brightness was varied, and the frequency was held constant, what they discovered was that the brightness was directly proportional to the rate of photocurrent. In other words, the brighter the light that shone on the metal plate, it removed more electrons per second, which was noted by an increase in the reading on the microammeter. When they performed the second experiment, varying frequency, therefore color, while holding intensity and brightness constant, they found that the frequency had no impact on photocurrent. So the frequency was not directly proportional to the rate of emission of photoelectrons. All right. What we're going to do is we're now going to go to our photoelectric effect simulation, and we're going to take a look at this in more detail. So flip over to your photoelectric effect simulation. Okay, so here we are at the photoelectric effect simulation. And a couple things that you need to set up ahead of time here. One, it should start out with your voltage on 0. Turn it up to some positive value, in the neighborhood of 2 volts would be fine. You're able to control the metal over here that's in the plates as any of these values right here. We'll just leave it on sodium. And I believe yours probably looks like this when you first start out. Check the second box, current versus intensity of light, because that's what we wanted to note the effect of here. Notice that the light is a violet color, about 400 nanometers, and we can actually vary that into the UV range and all the way down to the visible spectrum into the red and down into infrared if we wanted to. We're going to leave it at 400 nanometers. Because we are not going to vary color here, we're going to vary intensity so you can see this effect. So note, right now, no electrons are being ejected from the metal at all. We have no light, the intensity is 0, shining on the metal plate. But if we take now and vary the intensity, we start to get electrons ejected from the metal. And as we continue, notice over here in the graph, the brighter the light that we shine on the metal, and you can also notice the value in the current, the ammeter down here, is increasing. And it's increasing in a directly proportional way. Maybe your graph looks like something like this. Just click on this positive, expand the graph out until the line looks something like this so you can see it easier. And as you decrease the intensity, you can see It just slides up and down as you increase and decrease the intensity of the light. Okay? So what's the point? The point is, as intensity of light gets greater, the brightness increases, the reading, therefore, the amount of electrons ejected from the metal increases. This verifies the experiment that we just talked about. Pretty cool little simulation. All right, let's go back to the smartboard presentation. All right, now what we want to talk about are the electromagnetic wave theory predictions, and based on the experiments, did they turn out to be true or false? The first electromagnetic wave theory prediction is that the greater the intensity, in other words, the amplitude of light, produces greater photocurrent, rate of photoelectrons. According to the experiments we just performed, was that found to be true or false? And of course, that was found to be true. As all our notes have indicated so far, intensity brightness is directly proportional to photocurrent, and our graph that we just showed you on the simulation showed that. Why would that be? Because light of greater amplitude carries more energy, therefore removes electrons at a greater rate. They also predict that at very low intensities, dim light, photocurrent will not flow for a long time. In other words, they say there would be a large delay. Why would this be? Because they would believe that low intensity light means it doesn't have a lot of energy. So there would have to be energy buildup on that plate before removing the photoelectrons. However, when they tested this, that was found to be false. That the photocurrent started flowing immediately. There was not a delay, even at low intensities. Lastly, electromagnetic wave theory predicted that frequency should have no effect on the rate of photoelectric emission. And as we pointed out earlier, when they just varied the color and held the intensity constant, that was found to be true. So, what's the point so far? So far, the only crack in electromagnetic wave theory is the fact that this second bullet was found to be false. And that's pretty tiny and not very significant find, but nonetheless, it was a small find there on the behalf of scientists who believe that maybe light isn't just made out of a wave. Okay, maybe it's made up out of something else. Okay. All right, that'll end the discussion here on the rate of emission of photoelectrons. Come back for the photoelectric effect part 2 for more information.